Hello, everyone. So now we're going to move on to kind of the last big topic in 7A, which is thermodynamics. And as you will see, it's going to combine a lot of the ideas. It's not, completely something new that you'll be hearing, but it's going to combine a lot of the ideas that we've been discussing in 7A so far. So let's kind of first, so in this recording, I will introduce some of the necessary vocabulary and terminology that we will be using in this unit of thermodynamics in this model. And we will also look at work and exactly what does it mean to do work, particularly on a gas. Okay, so what exactly is kind of the basic principles behind thermodynamics? What is it a study of? And basically it's the study of transfer of energy between systems and how that energy results in some kind of movement or change in the system. So how does the system respond when energy is being transferred to it? So again, something familiar, something that we've been doing all of 7A so far. So an example, if you heat something, one thing that can happen, it can expand. So this is something we haven't really looked at it too much detail. How does heating a gas change its volume? What we've been mostly focusing on is how is heating something change its temperature, or is there phase transition perhaps that occurs? Okay, so here just a couple of scientists that were involved in creating thermodynamics, and I wanted to point them out because their last names should be familiar based on the different units and things that are named after them. So Carnot, there's a Carnot cycle. I won't talk about it today, but you might see that showing up on some of the practice quizzes and things like that. So as you see, he didn't live for too long, but he made many significant contributions to thermodynamics. There's James Joule. So Joule is the unit of energy is named after him. Kelvin, the unit of temperature, and then Boltzmann constant, and we'll hear more about Boltzmann when we talk about entropy in the next week or so. All right, so there are these laws of thermodynamics. We'll focus mostly on the first and the second law. So what is the first law of thermodynamics? It might sound a little intimidating at first, but actually we've already talked about it this class. So first, let's think about energy and how it can change. So you have some system and you can calculate its change in total energy if there's some kind of interaction going on. So these are some of the energies that could change: thermal, bond, atomic, and nuclear. We haven't looked at those. Those require much higher energies. And then mechanical. So thermodynamics only deals with internal energy. These are all internal, where mechanical has to do with energy associated with the motion of the whole system. So we're not going to look at the motion of the whole system, like whether it's kinetic energy or potential energy, where it's located, but only internal energies, and specifically only the thermal and bond, because that's the scale of energy we want to focus on. So the first law of thermodynamics is basically just another way of stating conservation of energy that we've looked at so far, but specifically constrained to internal energy, which we, instead of using the letter E for energy in general, we use the letter U. So you'll see U showing up quite a bit from now on, but really it just means internal energy, so E. So U will be, for example, thermal energy or bond energy and so on. So first law of thermodynamics looks very familiar. The total change of our internal energy equals to Q plus work. So one thing that will be somewhat new in this unit is, so far when we looked at changes in internal energy, we have mostly focused on heat being the source of transfer. And when we've looked at mechanical energies, that's when we introduced work. But now we're going to actually see how work can also have changes on internal energy, not just mechanical energy. So we will focus much more on work, and we'll even look at processes where both heat and work is involved. Okay, so kind of a preview of the second law of thermodynamics, which I won't discuss until next week, is the fact that, well, conservation of energy is really not enough to explain all phenomena. For example, and this came up in DL, I believe, in one of your FNTs. What about a question like this? Why doesn't the dropped ball, so, or balloon, so there was I think an FNT question where a balloon dropped from the top of the physics building and you calculated the transfer of that potential energy of the balloon to thermal energy. So potential energy went down, thermal energy went up. That's how our energy was conserved. So why doesn't the balloon cool down and leap back up in the air? So if you think about it, just if the only thing that you had knowledge of is conservation of energy, this should happen. Why can't thermal energy go down and potential energy go up? It does not violate conservation of energy in any way, but you know very much so know from your everyday life experience that this never happens. You don't just see things spontaneously leaping back in the air. So what this kind of tells us is that having this model alone, or this first law of thermodynamics, is not enough to explain everything. It cannot explain to us why that can't happen. Or another thing that we've learned is that energy is always transferred from hot to cold objects. So when two objects come in thermal equilibrium, their final temperature is going to be somewhere in between. The hot one will cool down, the cold one will warm up. So why doesn't the opposite happen? Why doesn't the ice get colder and the water get warmer? So again, one thermal energy goes up, one goes down. Conservation energy is still okay, so it's not violated, but again, we know that doesn't happen. Heat always flows from hot to cold. So that's what's going to explain these things to us, is what's known as the second law of thermodynamics, and that has to do with entropy, that the entropy of the universe is always increasing, and that's going to be our kind of very last topic of 7a. So it's just a preview, but we'll talk more about it soon. Okay, so some things that we need to define when we're thinking about different thermodynamic processes. So there are these things called state functions, and what state functions are, they're basically properties of our system at some given time. So for example, what could be a state function? We have our material at some time, we can measure its temperature, we could measure its pressure, volume, internal energy, enthalpy, entropy, and all these other things. Some of them we haven't talked too much about. So what's important, though, for a state function to make sense is the system has to be at equilibrium. So if it's, for example, if you're talking about volume and you had some gas contained in some fixed volume, but then you just open the container, how can you measure the volume of the gas? You can't, because it's in the process of expanding. Especially if it's a very quick process, we need to wait until the system reaches equilibrium. So this is a subtle detail. We'll go more into it soon. And then the changes in these state functions. So from, if you look at our system, there's some process that happens. It had some initial temperature, then finally it had some final temperature. It just depends on where you start and where you end. It does not depend on how you got there. How did you get to that final temperature? Did you heat it up, then wait for it to cool down and heat it up again, or it was just a one-step process? It doesn't matter. All that matters is here's your initial and final state. Now, there are some things that so basically state functions do not depend on the process. They do not depend, the temperature that your bucket of water has does not depend on how it got to that temperature. You know, how many times did it boil or freeze? It's just that temperature at that instant in time. But then there are some things that are process dependent, and that's specifically heat and work, because heat and work describe exactly that process, how that energy was transferred. So it's not a property of your system or object itself. Your system cannot contain certain amount of heat and work. It just describes how do you get between two states. You can describe it by the amount of heat and or work that was that entered or left the system. So it's things that we've all really discussed. We're just kind of organizing it in this language of thermodynamics. Okay, so let's get back to our bucket of water. So state functions are basically just observable. So something that we can measure, some equilibrium properties. Again, it has to be at equilibrium of this water in this bucket. So what can we measure? You can measure temperature, volume, entropy. We'll talk about it later. As I mentioned, pressure, enthalpy, thermal energy. You can measure its total potential energy. So, you know, even on an atomic scale, but, you know, as we saw that it's related to some of these macroscopic properties. So these are all macroscopic properties because now thermodynamics is the study of macroscopic properties. So we're no longer thinking of things on the atomic scale. So that's why it says total here. So that's how you kind of reach those macroscopic properties. So all of these are state functions. But, you know, if you look at this bucket, can you measure how much heat was added or work was done in this bucket? And the answer is no, you cannot. You don't know exactly how it got there. Again, unless you look back at the beginning of time, Big Bang, and starting from there, if it would be possible, you know, you could trace all the processes that happened that finally gave you this bucket of water. So state functions have some instantaneous value that you can measure at that instant of time, as long as your system is in equilibrium, where processes cannot be measured. There's no such thing as the amount of heat or work that's contained in your system at some given time. So it's very important, this distinction between state function and process. It's going to be an important thing that comes up over and over in thermodynamics. Okay, so if we go back to this equation, what do we have here? So on the left-hand side here, it's something that it's the change of your internal energy. It's a state function, and it just depends on your initial and final state. So this delta is just final minus initial. You don't care about what happened in between. You're just looking at two states, and you're comparing the energy between these two states, where what's on the right-hand side depends on the process. So then to find Q and W, it does matter how you got from that initial and final state. So that's what we're going to look at. We're going to look at different processes, let's say, that can give you the same change in internal energy, for example. All right. So before we kind of move on into some more specific examples, let us now just define what work is, and work specifically in the thermodynamic model. So we've defined work previously when we looked at mechanical systems, or specifically how do you change the mechanical energy of a system by doing work on it, or what happens when work leaves the system. So we saw that it's related to force, and that's still the case here when we think about it in terms of work in within the realms of our thermodynamic model, and specifically work which is being done on a gas. So that's what we're going to look at. So let's look at this one example. One way that you can do work on a gas, again, it's related to force. So how can you exert a force on a gas? So imagine there's this container, and there's some kind of a lid which can easily move like a piston on top of this container. And inside this container is a gas that has a specific pressure. And pressure is related to force. So now imagine that you push down on this lid in such a way that the pressure outside is bigger than the pressure inside. So kind of the net force is downwards. What is it gonna do? That's gonna decrease the volume of your container. So in this case, we're adding work to the system. And what does that result in? It results in a smaller volume, thus higher pressure. And we will also relate this to the ideal gas law. And we'll see actually that indeed when you decrease volume, you're increasing pressure and you're increasing temperature in this case. So we're adding work to the system because there's a net force acting on the system. And that results in the change in thermal energy. So temperature goes up. And how do we write this then? We take our first law of thermodynamics and we can just rewrite that as change in E thermal. There's no bond energy going on here. It's a gas, it stays a gas. So the change in E thermal equals to work. There's also no heat. There's no external sources of, we're not heating this container. It's just a force which we relate to work. So work is getting put into that system. What does that mean? That thermal energy will increase, and we'll see it again later on. We'll see sort of a different explanation of this using ideal gas law. So volume is decreasing, positive work is being done on the system. Now the reverse case, let's take a look at that. Now imagine that there is some source, let's say of heat here, that results in a higher pressure in this container. So that higher pressure then, and outside now you're no longer pushing, exerting any force on the lid. It's just the external pressure, atmospheric pressure, for example. So by heating it, then the pressure inside the container will increase, which will result in a net force, which is outward. So there's work now being done by the system on the environment. So that represents work which is leaving the system. So now our equation is still the same, but now thermal energy goes down. So delta E thermal is negative and work is negative. So one volume is increasing, there's negative work which is being done by the system. All right, so let's actually now define work in terms of this pressure and volume. So for any given process where you start with some initial and final volume, so in order for work to occur here, volume has to change because you're either compressing the gas or the gas is expanding. And it turns out that work is the integral over pressure versus volume plot. So this is what this is, pressure versus volume. It's known as a state diagram, which represents a state. All a state diagram means it just represents a given process. So there's some initial state, final state, a process, and the direction of the process. These are the three things that need to be present on a state diagram. So we see that's our initial state here, that's our final. This line represents the process, how we got from the initial and final, and the little arrow, well, it's written here initial and final, so the arrow is sort of redundant. Sometimes you just see the arrow without the words initial and final. You just need to somehow indicate the direction of the process between the two states. So the area underneath this is equal to work. So it's written, the area underneath it is an integral. It starts from some initial volume to final volume. This minus sign tells us that when volume is increasing, work is being done by the system. So work is leaving the system. So if we go back here volume went up and that gave us negative work. So that's why you need this negative sign. When volume goes down, you have to get positive work. So when delta V is negative, it multiplied by this negative sign, we get positive work. Now, a simplification of this general equation for work is when, imagine a case when pressure is constant. So if pressure doesn't change with volume, it's just a constant, you could kind of pull it out of the integral, and then we just get, another way of thinking about it, you just get this rectangle, and we know how to calculate the area of a rectangle. You don't need to do, a complicated integral. It's just height over width. The height is pressure, the width is delta V. So this simplifies to just minus P delta V for a specific case when pressure is constant. But we're going to look at various types of processes next. Let's kind of try to make a little bit of sense of this. So let's look at the simpler case just because it's easier to think about it. So what does this tell us? It tells us if the volume change is bigger, the work is bigger, and that kind of makes sense. You would have to do more work to change the volume of this gas more and more. So you have to kind of keep on exerting that force over some given distance, which means the work is increasing as you're changing volume more. So it makes sense that would be proportional to how much you've changed the volume. But you see, it also is proportional to pressure. So what's that telling you? That if you're trying to do work on a system which has higher pressure, it would require more work to have that same change in volume. So intuitively, one way of thinking about it, think about your bike tire. So if the bike tire has really a lot of pressure, so it's really high in pressure, you just pumped it up and you're trying to squeeze it, in other words, you're trying to do work on it to change its volume, it's quite hard to squeeze. Now, if the bike tire is not completely flat, I mean, if it was completely flat, then you wouldn't have to do any work. It's already in a kind of pressure, atmospheric pressure inside, but it's kind of getting there. It's much easier to squeeze it. So it requires much less work, basically, to change the volume of a gas that's already at a lower pressure. All right, so here I kind of introduced some of the important vocabulary that we'll need. Next time, we'll talk about ideal gas law and we'll look at specific processes and a couple of examples. All right, thank you for listening. See you soon again.